Good evening, ladies and gentlemen. Welcome to video 3 of topic 1 of unit 4, electric potential in work. This video is going to be covering the main ideas of chapter 6.3 of book 2. Recall that we are dealing with book 2 at the moment, not book 1. So, if you're reading anything on nuclear energy, you're probably in the wrong spot, so you should be doing with electric energy. Here are the learning intentions and success criteria for this chapter. Please pause the video and attempt to complete the KS table down there on the bottom left. Sorry, bottom right. Okay. So hopefully you got that done. So if we have a look at the learning intention here, we can see that I want you to be able to explain the difference between electric potential energy and electric potential difference and calculate those values. So this one has some very annoying language where everything sounds the same and it's only one word difference. So in terms of our criteria, we need to be able to define these things. We need to know what electric potential energy is, what electric potential is, and what electric potential difference is, and then calculate all those things as well. And I've just abbreviated it down to EPE, EP, and EPD. So we can see we've got a bit of knowledge here. We need to know what these are. If we don't know what they are, we can't define them, and we need to be able to do them. So we need to know the formulas and appropriate ways to calculate. So let's talk about electrical energy. Now, we covered this a little bit back in grade 8. This is a car battery. It's 12 volts. This is an 8-pack of 1.5 volt AA batteries. So if you put them all in series, head to toe, that would also be equal to 12 volts. Batteries in series, just add the voltages together. Here are two 9 volt sort of rectangular batteries that if you put them together you would get 18 volts. But this one here can start a car. This one here, one of these can run a fire alarm for several months. And this one here, if you put two of them together, can power your remote control for a TV or like a remote control car or anything to that extent, little radio toys, for several hours or so before requiring recharging. But you can't use this, even though it's 12 volts, and that's 12 volts. You can't use this to run a car. What's the difference? Now, voltage and energy are connected, but they are not the same thing, and so we need to understand what this difference is and where it comes from. So let's start with electric potential energy. As I've explained previously in class, when we lift something, we store energy in our gravitational field around the Earth. When we let that something go, the stored energy gets converted back to kinetic energy as the object moves through the gravitational field. Electric charges do the same thing, but in an electric field. If something is held in a high electrical potential state, when you release it, it will move to a low potential state. The field exerts a force. We saw that in a previous video. Now, in doing so, it's going to gain kinetic energy. It's going to start moving. And this is what happens in our circuits. Okay, so I'll put that up there so we can see here, high potential energy, low potential energy, it has to move. Same thing here for gravity as a comparison here. So this is what happens in circuits. Electrons move from high potential to low potential, but the kinetic energy in this case gets turned into useful stuff. Light, so you can see my lovely image here, sound, so you can hear my voice, heat, so that you're not so cold on these coming up to winter nights. Now this graphic is in your textbook as well, so you can find that around about page 170. Now to gain that electric potential energy, and we give electric potential energy the symbol U. It's going to be pretty similar to that idea of just internal energy that we talked about in our heat and electrical circuits units. Work has to be done against the field. So if the field is pushing down, you see here the arrows are going down, so that means work has to be done the other way, and by doing work we increase the electric potential energy. Okay? Now the work equation is uniform across all of physics here. Work equals force times the displacement or the distance that you move it. displacement's the better one, and that's what's actually inside your syllabus, so we're going to use that for the moment. But we learnt last week, or last lesson, that electric field equals the force divided by the charge, or force will equal electric field times the charge. And so we can do this replacement here, that to do some work in electric field equals the charge multiplied by the strength of the field multiplied by the distance you move in that field. Now, do note, this is not a provided equation, but deriving it is useful and pretty easy to wrap your head around. And that work done will equal the new potential energy. When the charge is released, the change from high to low potential energy will equal the work done by the charge. So if we do some work, then we're going to lose potential energy, and the opposite, if some work is done on it, it will end up gaining potential energy. So work done by lowers the energy, work done to increases the energy. Okay, so you got to think about where's the work going. Is it coming out of the thing or going into the thing? Okay. There is a very good table on page 171 that does help with explaining this comparison. Now, this work equation here, this original one, it doesn't in our syllabus, but you'll see this at university, that the force and displacement has to be in the same direction. So really the proper one is force times displacement times the cosine of the angle between the two, because you're looking at the cross product, how much force is in the same direction as the displacement. And so remember, if you take the cosine of 90 degrees, you end up with 0, so there's no work being done, and that's going to pop up again a little bit later. So for you guys, you need to know that work happens when things move in the opposite direction of the field. If it's off at an angle, you shouldn't see that, because the syllabus definition just has work equals force times displacement. But we will see that a bit more when we deal with gravity and linear motion in next year's course. So that's potential energy. Now let's look at electric potential. And the only difference here, and this is what I really don't like, is they got rid of an energy. That's the only difference in the words. I mean, electric versus electrical, but they sound pretty similar. But they are different things. Now, electric fields, remember, are not constant. The only time they're ever really constant is when you have two parallel plates, and then the field lines will be constant going through it, so the force will be constant. But electric fields are not all that constant, and so we want something that is independent of the charge. Okay, well, basically we just want some easier math. And this is electric potential. So electric potential is the potential energy stored per unit charge at any given point, and we measure in volts. We give it the symbol either delta V or V. The formula booklet is going to use V, but delta V has some advantages that we'll see as well. And the way we work this out is by thinking about how much work do I have to do to bring something from infinity all the way to this point. It looks like this. So it is equal to the work done to move a positive charge from infinity to some point, this delta V. And that's because we define that the voltage at infinity will be equal to 0, because it's infinitely far away. And so a lot of the times they'll just go, instead of using delta V, they'll just use V, because it'll be the same thing. Because remember, anything take away 0 is itself. Now this gets to electric potential difference. Okay. Sorry, I don't want to talk more about electric potential for a second. Electric potential energy then is the energy residing in a charged object. So that first bit is about the energy in a charged object, while electric potential is the energy per coulomb of any charged object. One analogy is to think about gravity. Okay, so gravity force is like electric potential energy. We each have a different force on us. I weigh a lot more than most of you, probably weigh more than all of you in class. So I've got more mass on me. I have more force on me than you guys do. But if we're all to stand on a table and just jump down, we would all fall at the same rate, because we all have the same acceleration. We have the same electric potential. Okay? the force per mass, or the acceleration due to gravity, is the same for all of us. So, electric potential energy, okay, is different, but the electric potential, okay, is the energy per unit charge will be the same. Okay, and the math that comes up in a second will make that a bit clearer, hopefully. I never enjoyed this bit. I do find the language a bit annoying. Now, bringing a charge from infinity to some location is pretty bunk. Like, it's not going to happen all that much, if ever. And so it's much more convenient to talk about potential difference between 2 points. The potential difference is the difference in voltage, okay, or electric potential, at those 2 points. And it's equal to the work done in moving a charge, a unit charge in this case, which is the proton, between the 2 points. So let's have a look at that. So the work done in moving a unit charge between 2 points. And we can see from there to there. That's it. Okay? So we just saw a formula for work back a couple of slides, and now we're saying that this is also equal to work, which is kind of useful. And the formula is just this. The voltage equals the change in energy, because we saw that work was equal to the change in energy, divided by the charge. Now note, this is about a unit charge, which is why we've got to divide it by Q, because if Q is equal to 1, then voltage and delta U will be the same. Voltage and the change in internal energy will be the same. But it's very rare that you're going to deal with 1 coulomb of charge. Okay? So I did say 1 proton earlier. No, it won't be 1 proton, it'll be 1 coulomb of charge. So definitely not a proton. I should fix that up. This is the formula we're going to use for all our electric potential calculations. If we're after potential difference, well, delta V will just equal delta U over Q. If we're after the potential, it's just V equals delta U over Q. This is the formula that's provided in the syllabus, so in your work formula booklet. And so just recognizing that this V and this delta V here basically mean the same thing, because whatever the change in voltage, whether it's coming from infinity or coming from some point we know, it will equal the delta U divided by Q. So let's have a look at an example on this. Calculate the potential difference, there's our V, when 15 joules of energy is used to move 2.5 coulomb of charge through a field in a wire. Okay, the bit on the end really doesn't matter in this case, but we can see the numbers there. Let me move the tablet and turn on the light. Okay. Just set this up so I can see my numbers here. We have here a potential, we want to find potential difference. So what is delta V, or just V, equal to? And we have our 15 joules of energy. Our work equals 15 joules, because we're doing 15 joules worth of work, which means that our change in energy, our electric potential energy, must also be equal to 15 joules. This is not given in the textbook. I'm just sort of doing this as an extra to show you this is a bit clearer. And we have here our charge of 2.5 coulomb. Q equals 2.5 coulombs. Alright, let's chuck in our formula. Delta V equals change in U over Q equals 15 over 2.5, and let's see, 2.5 times 2 is equal to 5, so times the ratio, that will be equal to 6 volts. Okay. So a 6 volt battery would be spending 15 joules of energy to move 2.5 coulomb across its potential difference. Remember, we could go and apply this to our other things as well. Remember, our delta U, okay, because it is equal to our work, is equal to our Q E D. And now we don't know E or D in this case, but we could make our substitution go that 15 equals 6 E D, and so our electric field and the distance it moves, and divide that by 6 is, well, that's equal to 2.5. Okay. And that's kind of an interesting thing here, because yeah, divided by 6 is, sorry, not divided by 6, oops, divided by 2.5. is equal to 6 volts there, is equal to 6. And so you can see here the voltage is going to be related to this ED here. Now that's not something that is required for you to know, but it does sort of help you clue in a bit that if we have some field and we have a distance that we move across it, well, that's the voltage. And then if we know the charge, that's the energy. Okay, so hopefully you can see that some of these pieces start to link together a little bit. Now the last little bit before we do our last example. So, we saw in a lab activity today, if you're watching this after I've recorded it, that when you have a voltage difference between 2 points, you have places where the potential is the same. So when we probed it, we found that the potential difference was the same in several points. And now these places of equal potential are called equipotential lines. And like we said with electric potential energy, you don't need to do any work to move along an equipotential line. So an equipotential line, set of locations with the same electric potential, and no work is done. Right, and here's a visual idea of this. Here's a 4 volt equipotential line with point A on it, and there's a 6 volt electric equipotential line. And if I was at B and I moved a charge to C, it wouldn't take me any energy. If I moved it to D, it wouldn't take me any energy. Now, what I mean by wouldn't take me any energy is that it wouldn't take me any energy to do work against the electric field. I would obviously have to do a little bit of work to accelerate, put a bit of energy to accelerate it, because it has a mass, therefore it requires a force to accelerate, to change its velocity. And if I have changed its velocity, I need to be spending some energy, because kinetic energy is still energy. And then when it gets to the other end, if I need to remove that energy, I need to do some more work. So I'm not saying that absolutely no energy, there's some magical free energy device. Those are bunk. Anyone who tries to convince you of that is lying. However, we don't need to spend any energy against the electric field. Okay? That's a very important distinction to keep in mind. Last example on here. So we've got here in figure 4, which is the figure from before. Oops, there we go. What are the differences in electric potential for those ones? Let's actually just do this verbally. I don't think you're really going to need me to put the numbers on there. VB take VA. Well, we can see the voltage at B is on the 6 volt line, and the voltage at A is on the 4 volt line. So 6 take 4 is equal to 2. Done. VC, well, C is on the 6 volt line, A is on the 4 volt line. 6 take 4 is equal to 2. C is on the 6 volt line, B is on the 6 volt line. 6 take 6 is equal to 0. So no voltage in this case. Okay, so, or no voltage potential difference, no voltage difference. Hopefully that sort of makes a bit of sense, but you can go and look at Walding's working out in the textbook if you'd like. But hopefully you didn't need me to write that down. Now, there's a really good summary table, and I've got it here on page 174 of the textbook. I doubt you're going to be able to see this with any sort of clear resolution. I can barely make out some parts of it, especially these pictures at the top. They're a bit dark. I really recommend you go look at it. It's on page 174, and read through the description of the cases below it to help wrap your head around the language. As you've just seen, a lot of the language is very similar to each other, and it's very easy to mix up some of the words, and you don't want to go, well, often some of the stuff that to work out electric potential energy, if you could work out electric potential from a question that's actually asking you to do electric potential energy, but not get the marks for it because you've worked out the wrong thing. So it's especially important, because I know a lot of my students are ESL. We really want to make sure that you're getting this language clear, because this is probably the most confusing part of electromagnetism in terms of the language, because the names are very uncreative and they all sound the same. Okay, so have a read of those cases. Make sure that you're familiar with what's going on with it and understanding the differences. All right. So to summarize off here, in this video we've done the following things. What's the difference between electric potential energy and electric potential difference? And then how to calculate electrical energy, work, end potential difference. For your entrance slip, please complete questions 1 to 7 in chapter 6.3 of book 2, not book 1, book 2. Check your learning PDFs, copy your answers for them into the 4.1.3 space on eLearn. Thanks for listening, guys. Have a great evening.